So in the first lecture, we had discussed about the introduction to AI. Now we are going to focus discussing on knowledge representation issues. So that is the next unit that we are going to discuss. So let me share and discuss with you. Okay. So as we started discussing with artificial intelligence, we had discussed that artificial intelligence is a very interesting field, and there are so many new projects, so many applications which are going in artificial intelligence area. Now, also we had discussed that AI is a kind of field where what you require is that knowledge representation. If you want your AI application to work very, very efficiently, then what you require is your knowledge representation should be very, very efficient. So in this lecture, we are going to discuss about knowledge representation issues. So this is, if you refer the Rich and Knight book, Artificial Intelligence by Rich and Knight, then this one is covered in chapter number 4. And if you refer to GTU syllabus, this is considered as unit number 3. Now, if you look at this, all images, what it is trying to convey to you. What is basically artificial intelligence? Artificial intelligence is making machines think and behave like humans in the fields where humans are doing better than machines. So what basically we are trying to do to make computers smarter in those fields, we have to provide the knowledge of those fields to computers. So humans are going to assert their knowledge to computers. And when humans are going to assert their knowledge to computers, what is very important? The knowledge that you provide to computer, the knowledge that you insert to computer, how much knowledge you provide, how efficiently you provide the knowledge to computer, that is very, very important. So this is what we are going to, we are representing here by these images, that we are trying to teach computers. Computers are trying to learn from us, and at the end we are trying to achieve that computers are going to behave as smart as humans are in these specific fields which we want them to. So what is basically importance of knowledge over here? So as we have already discussed that the main aim of artificial intelligence is making computers think and behave like humans in the fields where humans are superior. So the first question that we should ask is, which are all the domains we are talking about where the humans are actually superior than computers? So the following fields are few of the fields where humans are superior than computers, and they are accumulating knowledge, analyzing the knowledge, processing the knowledge, using common sense, learn from the experience and surroundings, unlearn, relearn, and as and when needed, learn it once again. So these are the fields where computers are behaving much, much better than, humans are behaving far better than computers. And these are the fields where we want to make computers smarter as we humans are. So let us take one example, that if we are talking about doctors, human experts, and we are talking about doctors, we know that doctors do have their domain knowledge in their own based ways. So if we want that computers should be behaving as good as the doctors do behave, like we want computers to behave like human expert, we want medical expert system. So what all knowledge we will have to assert to these computers? We have to provide all the medical domain knowledge to computers so that computers will be able to behave like doctor. Now that is not enough. We need not to just provide only the medical knowledge to computers, but we also have to make computers able to learn from its experience. We also have to make computers able to relearn and unlearn, because that is what doctors do. They don't only learn in their curriculum throughout whenever they are doing MBBS, but later when they are practicing based on their experience with the patients, They learn new things, they experience new things. There will be many things that they learn from the books which may not be relevant to their experience, and then they are going to unlearn that. They are going to relearn few new concepts. So that is all things you will have to make computers to do. So do you understand that here knowledge is very, very, very important, right? So that is the power of knowledge whenever you are implementing any application of artificial intelligence. So this is what we where we are showing that knowledge is very powerful. So in this unit we are going to talk only about knowledge and knowledge representations. So what is importance of knowledge representations? So see, our aim is very clear now, that we want computers to behave, think, act, analyze and process like we humans do in this specific domains where we are very powerful and we are very superior. To perform this, just gathering knowledge is not enough. Like it is not enough that we will have just all knowledge of that particular domains. But what is actually equally important, that whatever knowledge you have gathered from this problem domains, you have to represent that knowledge also very, very efficiently. So knowledge representation is also very, very important task. So what you have to do? You have to gather knowledge, then you have to write facts into appropriate, generalized, unambiguous format. That is called knowledge representation. Write facts. What next you have to do? You have to make sure that you are not going to miss out any information, miss out any fact, however silly, however negligible, however unimportant that piece of information or that fact may sound to you. Because you may feel this is very silly or this is very inherent and this is understandable, this is common sense, but that is common sense to you. This is not going to be common sense for computer. So everything, however unimportant, however basic, however primitive it is, you have to write that in form of facts, very clearly in unambiguous format. Okay, so this is very important. Also you have to write appropriate procedures, appropriate rules, so that whatever facts you have written, whatever knowledge you have asserted, that can be manipulated efficiently and new information can be inferred, new information, new facts can be extracted from whatever facts you have inserted in your knowledge representation. So this is what is very important to do for making any AI application. Gather all possible facts, don't miss out any information. Now after gathering the facts, represent those facts in a generalized format efficiently so that you can process that and infer new knowledge also. Now we are talking about the representations and mappings. So to solve any complex AI application, what you have to do? You have to gather large amount of knowledge. Also, what you have to do? You require some mechanism to manipulate these knowledge so that you can get the solution of whatever problems you want to deal with. So gather the information, gather the knowledge, and find out the process by which you can manipulate this large amount of knowledge. Okay. Now, knowledge representation has basic terminology that we need to discuss. So, the first thing which we have already discussed is fact. What is fact? Facts are the real world truths. Second terminology is representation of fact. So, what do we mean by representation of fact? A generalized format in which we are going to write our facts appropriately so that there won't be any ambiguity and that will be very understandable for everyone. Okay, whether the person is technical or non-technical, our representations should be generalized enough so that everyone can understand. So these two things are very basic thing over here: facts and representation of facts. Now the representation of facts is done at two levels. The first level is called knowledge level. What we do at knowledge level? At knowledge level we are going to describe our facts. So initially what we are going to do, we are just going to write our facts, describe our facts, and that process is called knowledge level. Okay. What is the second level? That is called symbol level. At symbol level, what we are going to do to represent our facts, we are going to have different objects, and we are going to represent the different objects with the help of different symbols. So representation of objects in form of symbols is done at the knowledge level. Okay, how we will see this example, so it will be more clear. So there are two levels: knowledge level, where you are going to just describe the facts in sentences, words, And then symbol level. Symbol level is the level where you are representing your facts in the form of, you will identify different objects, the relationship between the objects, and represent them in form of symbols. Okay. Now for performing all this at knowledge level as well as symbol level, there are two kind of mappings done: the forward mapping and the backward mapping. So what is forward mapping? The forward representation mapping is when you represent mapping from facts to its representation. Means whenever facts are returned in form of a generalized representation, that fact to representation mapping is called forward mapping. Okay, we'll see this with examples. It will be more clear. What is backward mapping? Whenever you are having a representation available and you convert that to English like statement, that is fact, it is called backward representation mapping. Let us see with examples, so it will be more clear to you. So if I say Spot is a dog, it's a fact. This fact is written in English like statement. Okay, we are right now discussing forward mapping, how we are mapping fact to representation. Okay, so what is forward mapping? Whenever you have a statement like Spot is a dog, that is a fact that will be converted to representation. What is going to be representation? So here what we will do, as we have discussed in the lab, we will identify the most generalized word. For us here, the most generalized word is dog. So what we are going to do? We are going to write dog in round bracket Spot. Spot is the specific information, the name of the dog. So dog in bracket Spot full stop. That is going to be your representation of knowledge, representation of fact. So what is forward representation? Converting this fact, English like statement, to its representation, dog in bracket Spot. That is called forward representation. Now take one more example. If we have a fact which says all dogs have tails, we are talking about in generalized form, all dogs are having tails. So as we are talking about all dogs, we will be using over here for all. As we will be writing more predicates in coming lectures, this will be very clear. You must have used this notation when you had studied set theory and all in mathematics. So this symbol is used to indicate for all. Next is the variable. So this indicates for all x, then colon, dog in bracket x. When x is a dog, it implies, arrow indicates implies. For all x, when x is dog, it implies has tail in bracket x. So here we have used two predicates because we need to indicate two information. We are talking about dogs and we are talking about dogs which are having tails. So dog in bracket x, where x is a dog and has tail x. So what we are trying to say that if x is a dog, then definitely x is also going to have a tail, right? So don't confuse this with prologue terminology. It is reverse. So what here we mean that if dog x is true, then only the right side, that is has a tail, x is going to be true. Means if x is a dog, then x is going to have tail also. So this mapping from fact to representation, from the statement all dogs have tails to for all x, dog x implies has a tail x. This is called forward mapping. Are you getting this? Okay, now what is deduction or inference out of these two statements? When I say dog in bracket Spot, and when I say for all x, dog x, then x can be replaced by the name Spot. If I do that, I am talking about a specific dog with the name Spot. So if I replace x by Spot, what will happen? Dog Spot, it implies has a tail in bracket Spot. So if the name of the x is Spot, I will replace everywhere x by Spot. So what I will get inferred, what I will get deducted has a tail in bracket Spot. Now this is representation. Now when you convert that, to understand what it means, you have to convert that to English like statement, means convert that to fact. So what is the equivalent fact in English like statement here? Spot has a tail. Are you getting this? So from representation, when you convert that to fact, means English like statement, from a has a tail Spot to when you interpret it as spot has a tail. This mapping is called backward mapping. So whenever we are going to represent our facts, we are going both ways. First of all, we'll have forward mapping. We will deduct something, and then we are going to have backward mapping as well. So forward mapping is converting facts to representation, and backward mapping is converting representation to facts. Simple, right? Okay. Now, so this is something which has been asked many times in GTO question papers for 7 marks. So please focus properly. Approaches to knowledge representation. Now there are two things that you need to understand. Approaches to knowledge representation is different, and qualities which these knowledge representation approaches should have, that is different. So right now what I am discussing is qualities, desired qualities of good knowledge representation approaches. After that we are going to discuss different approaches for knowledge representation. So, what are different qualities a good knowledge representation should have? So, there are four basic properties. So, this is also asked many a times in GTU paper. Discuss qualities that good knowledge representation technique should hold. So, there are four properties. The first property is called representational adequacy. What is meaning of representational adequacy? Your representation should be stronger enough to represent, ability to represent all possible knowledge in the domain. Whatever kind of knowledge your domain have, there can be versatility, there can be vast possibility of having wide amount of knowledge. Your representation should be stronger enough to represent all this knowledge efficiently. So ability to represent the required knowledge, that is called representational adequacy. What is the second property that your knowledge representation should have? Inferential adequacy. What is inferential adequacy? The ability to manipulate the knowledge represented to produce new knowledge corresponding to inferred from the original. What is meaning of this? What is meaning of inferencing? Inference means deduction. Whenever you already have knowledge available to you, you apply certain procedure or process and try to deduct, try to infer new knowledge. Okay, so what is meaning of inferential adequacy? The ability to manipulate the available knowledge and infer new knowledge and add that new knowledge to your knowledge base. That is called inferential adequacy. Infer as much knowledge as possible out of the old knowledge, which original knowledge that was available to you. That is called inferential adequacy. What is inferential efficiency? Only inferring new knowledge is not enough. What you have to do? Efficiently store back that new knowledge that you have deducted. So, ability to incorporate into knowledge structure, whatever additional inferred knowledge that you have gathered, it should be able to restored in your original knowledge base. That is called inferential efficiency. The ability to incorporate into the knowledge structure additional information that can be used to focus the attention to new knowledge into the database. Means you should be able to update your knowledge base by adding whatever new inferred knowledge you have derived by point number 2. Is it clear, everyone? So in point number 2, we are talking about inferring as much information as possible. And in point number 3, we are talking about whatever inferred knowledge is, it should be able to be efficiently stored in your original knowledge base, added to your original knowledge base. Okay, going back to the next quality, it is expecting acquisitional efficiency. So the ability to acquire new knowledge using automatical methods whenever possible rather than relying on humans to infer. So you should be having certain procedures, you should be having certain rules so that automatically you will be able to acquire new knowledge as and when it is possible. You should be able to solve the problem and get the solutions automatically through those procedures. And this is called acquisitional efficiency. So these are the four basic properties any good knowledge representation should have. This has been asked many times in GTO for 7 marks. Imagine you have to just write these 4 points and you will get 7 marks. So remembering the names of this property is very important to get these marks. Okay. Now this is something which is practically considered as qualities a good knowledge representation should have. So what we discussed earlier are the ideal properties we will be talking about, and these are the practical properties any good knowledge representation should have. So let us discuss them also. The first property that a good knowledge representation should have is the representations need to be complete, so that everything that could possibly need to be represented can be represented easily. Means your representation should not be missing out anything. It should be complete. It should have everything. All the facts that you had to represent should be represented completely. It should be complete. They must be computable. Means it should be possible to implement. It should be possible to apply standard calculations, computations. So your representation should make your represented facts computable, implementable in standard computing procedures. They should make the important objects and relations explicit and accessible. Okay, so that it is easy to see whatever is going on, how the various components interact with each other. So all the objects and relationships you have in your representation, they should be very clear, and they should be available, accessible to user, so user can understand, access, and process it very easily. They should suppress irrelevant details. Means whatever details are irrelevant to your domain, it should be avoided, so that unnecessary users focus won't be diverted. Okay, the next property that it should hold is it should expose as many natural constraints as many required, so that it will be easy to express how any object and relations are influencing each other, they are related with each other. So whatever kind of constraints you have, natural constraints are available in your problem domain, all the constraints should be specified properly, so that user will be very clear with the dependability of objects on each other, or dependability of objects and relationship, and so on. Okay, it should be transparent. Your representation should be very transparent, so that user can easily understand what you are trying to convey. Okay, the implementation need to be concise and fast. Your representation should make your calculation, implementation, your representation show so is simple, easy, and fast, so that information can be stored, it can be retrieved, and it can be manipulated, processed very fast, rapidly. Are you getting this? So these are the 7 properties a very good knowledge representation practically should have. Now, this is something which has been asked many times in GTU question papers for 7 marks. Okay. So please focus very clearly on this. There are 4 approaches, 4 ways how knowledge can be represented. So there are 4 approaches of knowledge representation. The very first and basic knowledge representation approach is simple relational knowledge. So what is simple relational knowledge? From your problem domain, you have to identify which all objects, entity. Object means entity. If I'm, let us say, talking about the college problem domain, then students are one of the entity, the faculties are entity, the admin staff is entity. We are talking about the relationship between students and faculties, student and admin staff, student and library is one of the entity. So everything that you deal with is an entity. They are related with each other with some relationship. So from your problem domain, you have to identify all the entities, you have to identify all the relationships, and store that in form of a table. Yes, a database or table. So for every entity or object, there is going to be one row. Let me give an example. For every entity, or you are going to store one row, and for all the qualities which entity is going to hold, you are going to specify one column. So let us say musician. There are 4 musicians available. So we have written their names and their qualities, which style they use, which instrument they are using, what is their age. It is called quality of a musician. So all these qualities or properties are stored in different columns. So how a relational knowledge is stored? Once again, identify the entity or object and store all the entity or object in different rows, unique rows. For all these entity or objects, you will have different properties describing these objects. These properties or qualities should be written separately as different columns. So this representation gives very little opportunity for inference. Very less reduction can be done, but it is very basic and very simple. So it is simple way to store facts. Each fact set of objects usually is stored in form of rows and columns. Very little opportunities there for inference and knowledge basis of the inference, but that provides the basis for simplest possible knowledge base to users. So if we take the example over here, then we have different entities available. So the object or entity we are talking about is musician. So different musicians are their names are written in separate column, separate rows to indicate different objects or entities and their qualities which define them, which describe them. Those properties are written as separate columns: style, instrument, age, etc. For example, if I'm talking about students, then I can have a student as the name of the column. Then let us say name of the student, city of the student, CPI, SPI of the student. They can be different columns which are describing a particular student. Now below that we will write name of all the students, and then in the columns we will write their appropriate properties. Simple. So that is called database representation, or we can say it as relational knowledge representation. Okay, so what kind of questions we can ask, what kind of answers we can get from this? We cannot infer new knowledge easily out of this because it is very simple and basic. But still you can get certain simple questions answers. For example, who all are dead out of all these musicians? So you can see the first one and the third one, they are deceased. So they are the musicians who are already dead. Okay, who plays jazz or trumpet? So again, you can identify that from this style. So you can identify jazz is played by the first one and the last one, and trumpet is played by the first one only. So if you are talking about the one who is playing jazz as well as trumpet, then it will be the first musician only as the answer. So these kind of simple questions can be answered using this representation, which is also called simple representation. Is it clear to everyone? Okay. So we'll move ahead a little bit now. So this representation is very popular in database representation. Moving ahead, the second knowledge representation is called inheritable knowledge representation. Now here we are going to add up this concept with the concept you already studied in C++ or Java, that was called inheritance. What is concept of inheritance? In the concept of inheritance, we imagine our problem domain in form of hierarchies. What is meaning of hierarchy? You have a class, you have a subclass, you have a superclass. Means you have a parent class, you have a child class, you have a sub-child class, and so on. So what will happen when you have such hierarchy? Suppose you have a parent class and then you have a child class. Okay. For example, we are talking about musician is a child class and person is a parent class. So person class is a parent and musician is a child. Then whatever properties a person class, parent class has, all those properties of the parent class can be inherited to the child class. That is musician. Are you getting what I'm trying to say? So inheritance is the parent class will be inheriting the properties to child class. Now there are two things. Either the child class wants to inherit all the properties, or child class may inherit few of the properties, and it will add on its own few of the properties which it don't want to inherit. Right? So this is the concept of inheritance we already know. So over here also, when we use inheritable knowledge base, what we are going to do, whatever problem domain we are working with, we describe our problem domain in form of hierarchy. And we try to derive which classes are super classes, which classes are subclasses, which classes are again subclasses, and so on. Then we try to see which properties are inherited to the child classes, which properties are adding their own values, and so on. So here the knowledge elements inherit attributes from their parents. The knowledge is embodied in the design hierarchy is found in the functional, physical, and process domains, right? So as I have said earlier as well, that parent may inherit properties to child, but it is not compulsory for the child class to inherit all the properties. The child class may inherit few of the properties and may have few properties of their own. For example, let us say that we are talking about let us say a family where the parents are having very height around 6 feet. So the child will have the probability of having the same kind of height. So child may also have the 6 feet height, or child may have any height between, let us say, 5'5", 5'7", or 6'2", 6'5", means its own property of height attribute. Are you getting what I'm trying to say? So either inherit the exact property, or have own unique value for that property. Both are the possibility for the child class. Are you getting what I'm trying to say? So surname is something child is going to inherit and not going to change. But then the other things the child may change. Okay. Now inheritance is very, very powerful form for inference, but it is not adequate. It is not sufficient. Apart from inheritance, you also require something called inference. Because from inheritance, few properties can be inherited, but when you want new information to be generated out of your structure, KR means knowledge representation. When you require that from knowledge representation, what do you require? You require some form of inference also. Now the example which we are going to discuss over here, that is also called semantic net. So there is a separate unit which we are going to discuss, which is called semantic network. Semantic net. It is also called group of frames, set of frames, collection of frames, and it is also called slot and pillar structure. So as a separate unit, we are going to discuss it, but yet as we have to understand inheritable knowledge, we are going to discuss this example. This example is very, very, very basic. Okay, fine. So we'll start discussing the hierarchy. Can you see the problem domain over here is the baseball knowledge problem domain. So let me try to explain you what this diagram is trying to explain. See here the super class is person class. So all these squares over here that you can observe, they are the entities, the objects or elements of the specific class inherit the attributes and value from the generalized class. What you can observe over here is the box nodes, the square or rectangles observed over here are either the objects or values of the attributes. Either they are objects or values. But the relationships or attributes are written on the arrows. Let me repeat. The square or rectangle boxes which you observe over here, either they are name of the object, name of the entity, or they are values. And the relationship between the object and the value, the relationship between them is written on the as a label on the arrows. So if we describe this hierarchy of baseball problem, then the most super class is the person class. Okay, it has one property which is called handed, and the value of this property or value of this attribute is right. Means the person is right handed by default. Any person by default is going to be right handed. So only attribute which this particular object or entity has is handed. Now we are talking about a subclass. Subclass is adult male. When we talk about adult male, then a specific attribute it is adding is height attribute. And what is the height attributes value over here? 5'10". Okay. Now we'll go back to the another subclass, that is baseball player. Adult male can be a baseball player also. For a baseball player, what specific property it is having? So it is having different attributes like bats. What is value of bats? Equal handed. Okay, equal to handed. Now why this value is not written in square bracket? Because this is a recursive call. What is meaning of equal handed? Means the value of bat is equal to whatever handed property you had earlier. Where is handed written here? You can observe which person we had the property handed. So what is the whatever is the value of handed, that should be copied over here. So bats will be right over here. Are you getting this? Okay, another attribute that baseball player is having is height. So mostly the baseball player are going to have height 6'1". See, the adult male is going to inherit height property also to baseball player. If this height was absent, then baseball player would have the height 5'10". But instead of inheriting height from parent, that is adult male, baseball player do have their own value of height, which is 6'1". Are you getting what I'm trying to say? If this node was absent, baseball player wouldn't have any attribute called height, then it would have inherited height from parent class, but it is having its own value and hence it is not going to use the inherited value. Another attribute it has is batting average. It is 0.252. Now this baseball player are again subdivided into two classes, subclasses, pitcher and fielder. Now this pitcher has its own property, which attribute which is called batting average. The value is provided over here, and fielders are also having their own property, attribute batting average. So that is also written over here. Now we are talking about another classes. They are three finger brown. See, three finger brown and PV is their pseudonym for specific players. A player has a specific pseudonym three finger brown, and one another player has a pseudonym PV Reese. So there are two players with these pseudonyms. Okay, now these two players are member of the team Chicago Club and Brooklyn Dodger. So the attribute which we have used for describing that team membership is team. So three finger brown belongs to the team Chicago Cubs and PV Reese belongs to the team Brooklyn Dodger. So if we read this in the inverse manner, then we can say that three finger brown is a player who belongs to the team. Team is the attribute, the value is Chicago Cubs. PV is a player who belongs to the team Brooklyn Dodger. Team is the attribute and the value is Brooklyn Dodger. Are you getting this? Now, three finger brown and PVDs, they are instances of pitcher and fielder class accordingly, respectively. What is instant over here? So see, there are two special words that you can observe over here, ISA and instance. So what is ISA and what is instance? Instance means class membership. It is something like when I write in curly brackets X, Y, Z. There are three values in a set, X, Y, Z. I can say X is member of the set. So this is membership. Similarly, three finger brown is the member of the class pitcher. There will be so many pitchers and one of them is three finger brown. Are you getting what I'm trying to say? Out of X, Y, Z, X is member of this set. Means three finger brown is member of pitcher. Similarly, P is instance of fielder class. So that is instance. Are you getting a little what I'm trying to say? So instance means class membership. Now, as we'll have to finish in 40 minutes because you are going to have a small quiz out of whatever concepts we have discussed. I'm going to finish the discussion right here. More about this inheritable knowledge about what is instance, what is ISA, and once again explaining this whole diagram and then discussing how inheritable knowledge works, inferential knowledge works, declarative and procedural knowledge works, knowledge representation works. We are going to discuss in the next lecture. Okay, so just after this, you need to go back. I'll finish this lecture here itself. And what we have to do is you have to go back to classroom. One quiz must have been right now uploaded in your classroom. You have to attempt that quiz before whatever quiz, whoever has attempted that quiz within half an hour, only after half an hour that will be deactivated. Only those students are going to get attendance, not otherwise. Also, the marks of this quiz will be calculated summatively as it had happened in earlier semester also. So that's all about today's lecture. Do attempt the quiz and see you in the next lecture. Thank you.